Let me share something with you that's going to sound completely outrageous at first. It's going to clash with what you were taught in school, with what you've read in best-selling science books, and with what you've heard narrated in countless science documentaries. The Big Bang did not happen. There was no absolute beginning, no instant of creation, no singular moment 13.8 billion years ago when the entire universe burst into existence from a point of infinite density. Before you click away thinking I've totally lost it, let me be very precise about what I mean. I am not rejecting the Big Bang theory. I am not claiming that the universe is not expanding. I am not denying the existence of the cosmic microwave background, nor am I saying that we cannot trace the universe back to an extremely hot, dense state, roughly 13.8 billion years ago. What I am saying is that the common picture of the Big Bang as a literal moment of creation, a singularity where everything began, is almost certainly wrong. That image is a byproduct of forcing general relativity into a domain where it simply does not work. When you apply the correct physics, quantum mechanics, quantum gravity, whatever the final theory ends up being, the singularity vanishes. The notion of a beginning evaporates. My name is Leonard Susskind, and I've spent my entire career working on the deepest problems in cosmology and quantum gravity. Based on that experience, I can tell you with confidence that the idea of the universe originating in a singularity is almost certainly false. Let's begin with what we actually know. What does the Big Bang theory truly tell us? At its core, the Big Bang theory states that the universe is expanding. Galaxies are receding from one another. Space itself is stretching and growing. If you mathematically reverse this expansion, if you rewind the cosmic film, you find that the universe was smaller in the past, denser in the past, and hotter in the past. About 13.8 billion years ago, the entire observable universe was compressed into a region smaller than an atom. Temperatures reached trillions of degrees. Densities were beyond anything we can easily imagine. This period is what we call the early universe, or the hot Big Bang phase, and we have astonishing evidence for it. The cosmic microwave background, the faint radiation that permeates all of space, is the afterglow of that hot, dense era. It's essentially a photograph of the universe when it was only 380,000 years old. As it cooled from trillions of degrees down to just a few thousand, the patterns imprinted in that radiation align with the predictions of the Big Bang theory with breathtaking accuracy. So make no mistake, the Big Bang theory works. It's one of the most successful scientific frameworks ever constructed. But it comes with a serious, fundamental flaw, one that physicists have recognized for decades. If you continue extrapolating backward, pushing the equations earlier and earlier in time, you eventually reach a point where the density becomes infinite, the temperature becomes infinite, and the curvature of space-time itself becomes infinite. General relativity predicts a singularity, a moment labeled T=0, where the laws of physics completely collapse. This isn't some trivial mathematical inconvenience. This is general relativity screaming at us, as loudly as it can, that it no longer applies. The equations explode. They yield infinite, meaningless results. The theory is failing. Many people hear the word singularity and assume that's simply what the Big Bang is, that the universe began at a singularity, that this was the creation event, the ultimate starting point. But that's a misunderstanding. A singularity is not a physical object or a real thing in nature. A singularity is a mathematical warning sign. It's a theory throwing up its hands and admitting, I don't know what happens here. You need a better theory. Think of it this way. Suppose you use Newtonian mechanics to describe the motion of a baseball. You throw the ball, and Newton's laws predict its trajectory perfectly. But then you ask what happens if you accelerate that baseball closer and closer to the speed of light. Newton's equations start producing absurd results. The mass of the baseball becomes infinite. The energy diverges. Does that mean there's a physical singularity when the baseball reaches light speed? Of course not. It means Newtonian physics is invalid in that regime. You need special relativity. The Big Bang singularity is exactly the same kind of issue. General relativity is not equipped to handle the extreme densities and temperatures of the earliest universe. You need quantum mechanics. You need quantum gravity. And when you include quantum effects, the singularity disappears. This has been understood at least conceptually, for a long time. In the 1960s, Roger Penrose and Stephen Hawking proved that general relativity inevitably predicts singularities inside black holes and at the Big Bang. But they also recognized that these singularities signal the incompleteness of the theory. Hawking himself repeatedly emphasized that the singularity is not physically real. It's a breakdown of the classical description. Quantum effects, whatever their precise form, must smooth it out, remove it, or replace it with something else. So what replaces the singularity? The honest answer is that we don't yet know for certain, because we don't have a complete theory of quantum gravity. We have promising candidates, string theory, loop quantum gravity, and several other approaches, but no final, experimentally confirmed framework. Still, we can make educated inferences based on what quantum mechanics already teaches us. In quantum theory, there are fundamental limits to how small and localized things can be. You cannot confine a particle to a region smaller than its Compton wavelength. You cannot compress space-time arbitrarily. Quantum fluctuations and the uncertainty principle impose hard limits on how compact physical systems can become. This strongly suggests that when the universe was extremely small, smaller than the Planck length, about 1035 meters, quantum effects dominated everything. Space-time itself became a quantum object. Classical notions of space and time ceased to apply. Instead of a singularity, you had something entirely different, a quantum state, a wave function of the universe. One particularly elegant proposal is known as loop quantum cosmology, which grows out of loop quantum gravity. In this framework, space-time itself is quantized. According to loop quantum cosmology, the Big Bang singularity is replaced by a big bounce. The idea is that before our current expanding universe, there was a contracting phase. The universe shrank to an incredibly small size, but not to zero, not to a singularity. Quantum effects generated a repulsive force that prevented total collapse. At the smallest scales, gravity effectively became repulsive rather than attractive. The universe rebounded, transitioning from contraction to expansion. From our vantage point, looking backward in time, we see the universe expanding from an extremely hot, dense state. That's what we call the Big Bang. But if it even makes sense to talk about before, there may have been a prior universe collapsing into the bounce. Is this picture correct? Maybe, maybe not. Loop quantum cosmology is still under active development, and there are unresolved technical challenges. But the core insight that quantum effects eliminate the singularity is almost certainly right. Another influential idea comes from the Hartle-Hawking no-boundary proposal, developed by Stephen Hawking and James Hartle in the 1980s. This concept is subtle, profound, and beautiful. They suggested that in the very early universe, time itself behaved differently than it does now. At the Planck scale, time can become what mathematicians call imaginary. Not imaginary in the sense of unreal, but imaginary in the technical sense involving the square root of -1. When time becomes imaginary, it behaves like a spatial dimension. In that regime, the question, what happened before the Big Bang, loses its meaning, much like asking what lies north of the North Pole. There is no before. Time smoothly curves around and closes off. There is no boundary, no beginning, no singularity. This idea is speculative, and its interpretation is still debated. But once again, it illustrates how quantum effects dissolve the singularity and undermine the idea of an absolute beginning. Now let me introduce something that makes the entire Big Bang question even stranger and more intricate: eternal inflation. This is one of the most profound concepts in modern cosmology. Inflation was proposed by Alan Guth around 1980, with similar ideas developed independently by André Linde and others. The basic premise is that the very early universe experienced a brief period of extraordinarily rapid expansion. In a fraction of a second, space expanded by an enormous factor, perhaps 1060 or more. Inflation explains why the universe appears so flat, so uniform, and so homogeneous on large scales. It also predicts the tiny fluctuations that later grew into galaxies, which we observe in the cosmic microwave background. But here's the twist. In most realistic models, inflation doesn't just happen once and end. It continues forever, or more accurately, it becomes eternal. Inflation is driven by a hypothetical field called the inflaton. When this field sits in a particular configuration known as a false vacuum, it causes space to expand exponentially. Eventually, the inflaton decays into ordinary matter and radiation. Inflation ends in that region, producing a hot Big Bang and a universe like ours. However, the inflaton is subject to quantum fluctuations. In some regions, these fluctuations can push the inflaton back up into the false vacuum state. When that happens, inflation restarts in that region. That patch of space expands exponentially, creating vast new volumes of space. Within those regions, further quantum fluctuations generate even more inflating regions. The result is a fractal, endlessly branching structure, a never-ending process. Some regions stop inflating and become pocket universes, like our observable universe. But other regions continue inflating indefinitely. This is eternal inflation. The implication is profound. There is no global beginning. Individual pocket universes have beginnings. Our own Big Bang occurred 13.8 billion years ago. But the larger eternally inflating structure, the multiverse, has no beginning in time. There is a theorem known as the Bordguth-Vilenkin BGV theorem, which states that even in eternal inflation, you cannot extend classical inflation infinitely into the past. If the universe is expanding on average, there must be a boundary. But that boundary is not a singularity. It's not a creation event. It's more like an edge, a region where classical spacetime breaks down and quantum gravity takes over. Beyond that edge, or before it, if that notion even applies, we simply don't know what exists. Perhaps it's a quantum cosmological state, a wave function of the multiverse, something beyond our current theories. Let me explain why I believe this picture, eternal inflation combined with quantum cosmology and no absolute beginning, is probably correct. First, it's generic. Almost every inflationary model naturally leads to eternal inflation. To avoid it, you must carefully fine-tune parameters. And in physics, when something only disappears through extreme fine-tuning, that usually means nature doesn't bother to fine-tune. It embraces the generic outcome. Second, this framework aligns beautifully with what we've learned from string theory. In string theory, there exists what I've called the string landscape, an enormous collection of possible vacuum states, perhaps 10,500 or more. Each vacuum corresponds to different physical laws, particles, and constants. Eternal inflation provides a mechanism for exploring this landscape. Different regions of the multiverse settle into different vacuum states. The result is an infinite multiverse with immense diversity. Our observable universe is just one bubble among countless others. We observe the laws we do because only in regions like ours can observers exist. This is the anthropic principle, and while it unsettles some physicists, I believe it's likely correct. Third, this picture resolves deep philosophical puzzles about initial conditions. In the traditional Big Bang model, you must specify the universe's initial state with incredible precision. Why those particular values? The theory offers no answer. In eternal inflation, initial conditions don't matter. Whatever the multiverse began with, if that question even makes sense, eternal inflation erases the memory of those conditions. Every possibility occurs somewhere, and we find ourselves in a region compatible with our existence. Now, I know what you're thinking. You're thinking, Lenny, this sounds like untestable speculation. Multiverses, quantum cosmology, imaginary time. How can any of this be tested? That's a fair concern. We can't directly observe other pocket universes. We can't yet probe the Planck scale. We can't watch a bounce or measure imaginary time. But we can test the framework indirectly. Inflation makes concrete predictions about the cosmic microwave background, the spectrum of fluctuations, gravitational waves, and the geometry of space. And so far, those predictions have been spectacularly successful. Loop quantum cosmology predicts subtle imprints from a bounce that future observations might detect. The string landscape and eternal inflation make statistical predictions about which types of universes should be common or rare. These tests are difficult, but not impossible in principle. Most importantly, the alternative, the claim that the universe began at a literal singularity where physics breaks down, is definitely wrong. We know it's wrong because the very theory that predicts it tells us it has failed. So we're not choosing between a testable idea and pure speculation. We're choosing between a framework that certainly breaks down and one that may be correct, even if it's harder to fully verify. Let me share a personal story. Early in my career, when I worked on black hole thermodynamics and the information paradox, many physicists thought it was a waste of time. Black holes and information seemed like abstract curiosities, but quantum mechanics insisted that information cannot be destroyed, while general relativity said it is lost in black holes. Something had to give. Over decades of work, by me, by Hawking, by 't Hooft, by Maldacena, and many others, we discovered that general relativity was the thing that had to change. Black holes are more subtle, more quantum, more informational than classical relativity suggests. The Big Bang is the same story. General relativity predicts a singularity. Quantum mechanics says no. Something must give, and I'm confident it's the singularity that disappears. The real universe does not have a beginning in the way we usually imagine. There was no moment of creation, no first tick of time. Instead, there is an eternal quantum structure, perhaps a multiverse, that has always existed and always will, continually generating pocket universes like ours through eternal inflation. Does this mean the universe is infinitely old? Not exactly. Time itself may be emergent, a feature of the low-energy classical description. At the Planck scale, the very concept of time may lose meaning. Asking how old the multiverse is might be like asking what time it is at the North Pole. The question presupposes a notion of time that doesn't apply. What we can say is this: our observable universe has a well-defined age of 13.8 billion years, but the larger structure that gave rise to it does not have an age in the same sense. It may be timeless, eternal, or beyond time altogether. So let's return to the phrase the Big Bang. If by that we mean the hot, dense, expanding state the universe occupied 13.8 billion years ago, then yes, the Big Bang absolutely happened. The evidence is overwhelming. But if we mean a moment of creation, a singular beginning of time, a universe emerging from nothing, then no, that almost certainly did not occur. That idea is a misconception born from applying general relativity where it doesn't belong. Properly understood, the Big Bang is not a beginning. It's a transition, a phase change. It marks the moment our pocket universe shifted from an inflationary state to a hot, expanding one. Before that transition, if before is even the right word, there was inflation, quantum cosmology, and a deeper layer of reality we are only beginning to grasp. When I teach cosmology, I always warn students about the word before. It's a dangerous term. It smuggles in assumptions that may not hold. In general relativity, time is part of space-time, not an external backdrop. When space-time itself becomes quantum, the notion of a clear before and after may cease to exist, just like north ceases to have meaning at the North Pole. This is deeply counterintuitive. It clashes with our everyday experience of time and causality. But after decades in physics, I've learned that when the mathematics tells you something strange, you should listen. Nature is not obligated to respect our intuitions. So let me conclude by returning to the provocative title, Why the Big Bang Never Happened. The conventional image of the Big Bang as a moment of creation, a singular explosion from nothing, is wrong. The universe did not begin. There was no first moment of time. The Big Bang as a singularity never occurred. What did occur is that our observable universe transitioned from an inflationary phase into a hot, dense, expanding phase about 13.8 billion years ago. That event is real. It's measurable. It's one of the most important milestones in our cosmic history. But it is not a beginning. It is one chapter in a far larger story, perhaps a story with no beginning at all. Cosmology is moving toward a vision of an eternal multiverse, driven by eternal inflation, producing countless pocket universes, each with its own Big Bang but no global origin. It's a vision grounded in quantum physics, where time itself emerges, and the idea of a first moment no longer makes sense. It's a strange picture. It's deeply counterintuitive, but it's a picture forced upon us by the mathematics, by the physics, and by the fundamental structure of reality. The Big Bang never happened, not in the way you've been told, and understanding why is one of the great intellectual triumphs of modern science. Thank you for listening. The universe is far stranger than you imagine.